All right. Thank you, everyone, for joining me for another episode of Handmade Hero. You know, I've been doing this yesterday and today. I sort of started with the same thing I normally close with. I think I normally say "Welcome to Handmade Hero," the show where we code a complete game live on stream. I don't know why I switched it up. Maybe this weekend it's just backwards weekend. It's hard to say. Anyway, it's lighting time. We actually fixed the lighting yesterday to not have some obvious bugs in it that it had when we had just kind of splattered it in there. So we have a lighting solution now that, while it's not particularly interesting, it is actually usable at this point, right? Like, we're getting to the point where we could actually use it, and it's not good. Like, it's not what we want because it's pretty boring. It's pretty basic in terms of what it does, but it's getting there, right? It's like, it's not completely messed up anymore. And so that's a good place to be, obviously. But that just means our job for today and probably next weekend as well, before we decide to sort of get this down to a more optimized thing that we can use and put it on the GPU, which is going to be kind of the final phase of it. And that phase is, going to be pretty straightforward, but annoying because it involves GPU programming. Before we get to that, what we want to do is push the quality level a little bit here. And there's a bunch of things that we probably want to fix in terms of quality that I see, right? So looking at it at the moment, we get this kind of situation where if you take a look at what's happening, there are some basic things that I would like to try and improve on. So the very first one, obviously, is if we take a look at how these lights are distributing, you can kind of see how this light, for example, propagates basically symmetrically around where we're going. Like, for example, if I stick my guy right up against the wall there, you can kind of see how this square, which is 2 away, is lit basically the same as this square over here, right? There's really not a lot of difference between these. So you can put a light right up next to a giant occluder, and this is the only light in the scene, remember, and it will just bleed right through. And why does it do that? Well, the reason that it does that is because we don't really have any notion of shadowing in terms of light source direction. And so I don't love that aspect of what, we're not really doing that in there, which is bad. So I think we want to try to improve that. And the other thing is that you'll notice, like, I'm not getting as much color bleed as I would like. And so, if we take a look at what's going on here, where we've got this sort of lighting, where we're lighting some of these panels up, like right here you can see, you've got a lot of light shining off of these red panels, and I see almost none of it coming up onto these ground reflectors. There's maybe a tinge of it in there. If you really wanted to see it, you could. But in terms of if we're being honest about it, it's really not there in any appreciable way. If we take a look at the reflectors and what we're seeing, they're more or less, it's like those red ones aren't even there. And that's not what we want either. So that's really what we're talking about here. And so we need to sort of look at that. And so the two things that I would like to do is to push forwards is, one, I would like to start getting some directional shadowing in there. I don't like the ambient occlusion pass. It's turned off right now, if I'm not mistaken. Let me see if that's true before I say that, but I'm pretty sure it is. I don't like the ambient occlusion pass. We kind of got it from the paper, the Friction Labs paper. I don't like it. It's not doing it for me. Maybe that's because we implemented it poorly. I don't know. I mean, it's hard to tell without a reference implementation, obviously, but I don't really like it. I want something that's going to be better than that for shadowing. And so, if I turn that on here, here's the shadowing. Not a lot of difference. And you can see we get some weird behavior too. So we might have some bugs in there we could take a look at, just in terms of the fact that, you get this sort of pure black shadow where the light gets, clipped out entirely. I guess that could be theoretically correct, I mean, in a certain way, because if you think about it, this guy right here really has no one he can get light from. There's nothing to bounce off of. Oops. there's nothing for that light to bounce off of, like nothing nearby for it to illuminate. So when it gets shadowed, it can be shadowed entirely. So that, I don't necessarily think it's wrong. And when we put together a more realistic scene that had, a ceiling or a skylight, I think you wouldn't have that problem happening as often. But the thing that I would point out is I'm less inclined to go diving into the ambient occlusion pass and try to find if there are bugs in it, because I don't like it to begin with. Because as our shadow, if that's our solution for shadows, well, it doesn't work and isn't going to work, because the thing about ambient occlusion is it doesn't have directional shadowing information in it. It doesn't know if you're on one side of a wall or not. And so the problem that we will just have with it, whether or not it's working well, is that it will never produce the actual shadowing results that we want. So at best, that ambient occlusion thing can only really be part of another algorithm that would do the other sorts of things that I want. And so I'm less inclined to really deal much with it at this point. I would probably just say we're going to leave it kind of off on its own. And we'll revisit it if we feel like we need what it does later on. So what I'd like to do now, again, is, start to focus on trying to improve the quality there. And I think what I'd like to do is maybe try to focus on that shadowing quality. It does bring up one question of whether or not we need to make the heroes not interpenetrate with really tall walls. I don't necessarily know if there's much we can do with that. It's a good question. Yeah. We're going to have to I swore on the screen. We're going to have to mess with our Z-bias. That's like the 5th one. Man, I tried so hard to not have any curses on the stream, and I fail. So anyway, here's what we need to do. We need to start looking at improving that lighting. And what we want to do is focus on either the shadow or the light bleed part. I think both of them are fixable, and we can start to play with them. What do I think these are coming from? Well, first of all, the shadow part is really obvious where it's coming from. It's a lack of something. Right now, the light just propagates light between surfaces without thinking about whether there's something in between the two surfaces that are trying to provide light, right? So what happens in this case, what we get is a situation where each of these reflectors, and again, I guess I should go back to the reflector view so you can see it. Each of these reflectors is transferring light between every other reflector, right? And we will do something that reduces the degree to which we n squared that in the future, but for the moment, it doesn't matter because we're actually even doing it n squared, and that's fine. Like, we're just for testing, we're doing it n squared. So when we're doing this n squared transference, the problem that we will run into is that if we are just testing each one of these reflectors against each other reflector, right, then we really don't have any way of knowing whether or not that reflector can see the other reflector. We know if the reflector is too far away, right? So when we're moving the light around, we do know stuff like, oh, okay, this reflector isn't getting much light from this light source over here, and the reason is because it's too far, So that's a pretty easy way for that to be rectified and get, that sort of information about lighting fall off into place. What we don't have is a way of knowing, well, this can't really see this because there's stuff in the way, right? And so the amount of light that comes back here should be lessened. That's just a basic part, no matter how we do our reflectors or how they're shaped. That's something that we just need some way of taking into account. So what I want to know is there some way that we can take what we're doing right now and change the basic idea so that we end up computing something that has a little bit of shadowing in it. And I guess I might suggest something really ridiculous at this point, which, I guess it's one of those things where you never really know till you try. Um, but if we imagined that every reflector was actually going to sort of keep a little bit of a pseudo pixel render kind of a thing going on, I know this sounds ridiculous, and yeah, I know this sounds absolutely ridiculous, but if you imagined that we just sort of took every reflector and looked at how the other reflectors mapped onto its hemisphere, that is sort of the complete picture of how the light comes into that reflector, right? Because the thing that we're not capturing now that we need to capture is the fact that reflectors overlap, and so if we took, almost a rendering of that hemisphere, then we would get, that information that we needed, right? However, that's like cost prohibitive to produce. Even if we were on the GPU, if you imagine that we have something on the order of 5,000 of these reflectors eventually, rendering 5,000 cube maps or something is probably not a very good idea. Even if we were to do it sporadically, and even if we're doing it just with flat plates like this, 5,000 times 5,000, in terms of the render load, isn't necessarily that bad for a GPU, right? Like if you're trying to sync, what would that be? So it's 25 million. If you're trying to sync 25 million primitives, well, honestly, since they're instanced, because you're rendering the same 5,000, just rendering them 5,000 times, is really not that bad in terms of the number of primitives you're trying to sync. The problem is the number of destination cube maps there, and the setup involved in switching render targets 5,000 times sounds dangerous. So in terms of actually rendering all of the reflectors in that sense, I don't know, that sounds pretty rough. So, the question is there something we can do that's more straightforward than that, that's simpler than that? And I don't know, but let me just sort of give you an idea. Milton. All right, so here is the problem. And I'm going to draw it right here. So the problem that we have is we've got these reflectors, and we want to take a look at, some other set of reflectors that are coming into it, right? And what we'd like to do is we'd like to be able to say, well, okay, so, this one is basically entirely behind these other two, so anything coming from this one just isn't going to be seen, right? The only way you're going to see any contribution from this one is if it, secondarily bounced off something else you can see, like maybe something over here or something like that. But you're never going to see any light from this guy right here reflected onto this one. It's just not going to happen. So, the reason we're not getting that right now is because when we consider these two, all we look at is the distance. So the fact that this one happens to be that far away is the only thing that attenuates it. The fact that these two are in the way doesn't really help us, right? And similarly, if we take a look at the ambient occlusion pass, the ambient occlusion pass just looks at how much these other things shadow the hemisphere of this guy. It doesn't tell us for which person. It doesn't tell us that this one is shadowed more than this one, which is the information that we actually need. And so from this reflector, what we'd like to do is we'd like to actually say, well, tell me about what all of these reflectors would flatten onto if I was to draw this hemisphere in here. And again, what we could do, right, like I was saying, is we could take a cube map, and we only need, 5 of the 6 sides of the cube map. Obviously, this back face here is not relevant, but you get the idea. if we were to look at this cube map and say, well, what's coming in on the cube map? What's coming in on the cube map would tell us this information, because each of these things would project onto the cube map and they would be z-sorted. So the z-buffering of the cube map would take care of that piece of information for us that we actually need to know. The problem, of course, is that we don't have probably the resources to render an entire cube map for each of the 5,000 reflectors that might be in one of our scenes. Now, maybe that's a stupid statement. Maybe the real statement is, no, of course you can do that. Welcome to the new GPU land. Just, of course you can render 5,000 cube maps a frame if that's the only thing you're really doing. Go nuts. You're right. Because again, we don't need to send out any additional information for this, because all 5,000 primitives are the same every time, right? They're the same set of reflectors. They're just being viewed from a different viewpoint. So it's really not that big of a deal. I don't think that's really that sane of a statement to make. The reason is because, again, the cube map itself is actually 5 faces we're going to have to render. Rendering 5 faces of a cube map means actually 5 render passes. So in effect, unless we actually try to do it a little bit more straightforward, where we actually set up multiple render targets, which we could probably do, and then render everything to the cube map incrementally in that way, I don't know. It's kind of a nightmare, right? It's not great. So what I'd rather do is try to think of some scheme that we can do that's not quite so bad as this, right? It's not quite so bad as this, but maybe does effectively sort of, maybe a little bit, sort of, kind of, maybe a little bit, kind of the same thing. And there's a pretty straightforward way we can actually do that, and the only problem with it is it's probably a little too artifact prone. I'm a little worried about how you would get rid of the aliasing on it. And so I guess we could just try it. I don't really see why not. There's not a reason not to try it, I guess. But it's definitely one of those things you look at and go, well, okay, but yeah, how am I going to get rid of the aliasing on it? And I don't know the answer to that question. Maybe one will present itself. But here we go. What if we were to say, okay, we know we want to render effectively a hemisphere. Well, what does rendering actually do for us? What does rendering a cube map actually do for us? And at this point, you can see by the fact that I'm gesturing wildly that the coffee has kicked in a little bit too much. That's one of the cons of drinking coffee on stream, is you definitely elevate the energy level to an uncomfortable amount. But sometimes programming requires elevating the energy level to an uncomfortable amount, and that is where we are at right now. So I apologize that this explanation is a little bit too excited. That's just what happens with caffeine. Actually, it's more sugar. It's really the sugar. The caffeine's not so related. This is actually one of those Starbucks beverages that's mostly sugar, so the sugar definitely helps. Anyway, so looking at this, what I would encourage you to think about is what actually happens when we render. Why does rendering even solve any of these problems at all? Well, the thing that solves the problem is actually the z-buffer, right? The z-buffer is the thing that actually solves the problem, and it's no accident that the things we want to do with when rendering solves our problems, rasterization, I should say, solves our problems, the z-buffer is really the thing that takes care of it, right? Because if we were to render the cube apps in here, the thing that's telling us that we're going to have these things stacked on top of each other and that this one is going to be seen more than this one is the z-buffer, occluding per pixel those primitives, right? That's what's actually happening there. And so the thing to remember in that case is that the same is true for the lighting as is for the rasterization of the sprites and everything else. The z-buffer, or that depth store, is what is making this work. And so, for example, even when you look at doing things that have nothing to do with radiosity or the stuff that we're playing with now, if you look at how people do shadow mapping, for example, the same thing is true. It's basically using the z-buffer as a technique to produce what a light source can see, for example. And so rasterization, the key is the z-buffer. The z-buffer is the magic. That's the thing that's actually producing the information we actually need out of this process. And so the question we have to ask ourselves is, can we get the magic of the z-buffer in some way that doesn't require setting up a full render, worse, a full render from a cube map, no less, which is obviously not what we want because it's even more expensive than a regular render pass, and that's no good for our purposes. Well, the answer here, I think, is yes, we can. And the reason I say that is because the z-buffer is nothing more than a check per pixel to see whether or not the z-value of a primitive along the ray of a particular line of sight happens to be in front of everything else that has previously been seen. All it is one if, right? That's all it is. If you can tell how far away something is, you can do an if statement and say replace the current one with the new one if the current one's closer, right? That's all the z-buffer is actually doing for us. We don't need it to do anything else in this circumstance. So what I would say is, what if we just emulate that ourselves? So suppose we took and we said, here is our reflector. We would like to measure, and maybe I should draw this in 3 dimensions just to be clearer. So suppose I have my, here we go, something like this. Suppose I take my reflector and I say, I'm going to sample this reflector along some set of angles, I'm going to randomly pick some ways around the hemisphere to sample. When I say randomly, I don't mean that we're eventually going to use a random number generator to do it or anything like that. What I mean is, well, that's left as something to figure out another day, right? So let's just say we figured out the way that we want to sample this, probably using something actually fairly structured, because we're going to want to make sure that it's clean. So it's probably going to be something like a blue noise pattern across a hemisphere that we control actually fairly tightly for various reasons. That's something I don't even want you to think about right now. So let's just assume that we've done some work to figure that out and that work will get actually done in the future. We've got some series of rays coming out of the reflector that we want to sample. Effectively, we are ray tracing at this point, right? And now we're going to turn that z-buffer around and say, well, if we were doing a ray tracing approach, right, you're just doing the z-buffer but sort of doing it along a ray. So instead of producing all the primitives for a pixel, you instead are casting a ray out and saying, what does the ray hit, right? It's basically just ray tracing at this point, and it's turning that z-buffer around. Well, if we were going to do that, we could certainly ray trace our rays against our reflectors. If we have a definition for a reflector that allows us to intersect a ray with it, then we can do this operation fairly trivially, right? There's nothing magic about it. So we can effectively ray trace. Even on the GPU, we could ray trace fairly easily by just switching around the way the primitives work. We're saying each primitive is actually going to do a ray trace in the buffer to figure out what's going on for that particular pixel, right? There's ways we can set this up on the GPU to work, so we don't really have to worry about the fact that it's appears to be something that's ray tracing, because GPUs are so programmable now that we should be able to convert the algorithm over. So if we think about this as more of a ray tracing kind of problem, and we sort of invert it and think of it as looking outward, we can pick arbitrary directions, and we can pick a very small number of them potentially, right? We could say, let's suppose we've got 8 directions or 16 directions or something like this. That might be enough to give us a reasonable lighting solution while still not being too many for performance purposes, right? I don't know. It's just a suggestion, right? And furthermore, we are really only doing this to capture shadow information, so we are still taking into account the lighting from every reflector that we can see. We're just doing a set of quick checks on each of them to see whether or not we should maybe discard part of or all of the lighting information therein, right? Okay. The other thing that we can do here is take a page from the playbook of the original algorithm and say, well, what if instead of doing that, we actually considered them to be solid angles instead? So for example, let's say we wanted to do something where we have this reflector, like I say, and we want to do a cast outwards, and we actually consider each of those casts to be more of a cone. So what we're actually going to do is sort of take a look at how much of the cone is occluded by each of them, right? And so we can sort of talk about how much of the cone has been restricted at each individual place, or how much of the cone is being seen by one thing or another, that sort of a thing. And we can come up with some kind of ridiculous algorithm potentially that tries to weight contributions of things along the cone, right? So that's just my thinking of how we might be able to improve this algorithm. Maybe shoot out 8, shoot out 4, shoot out 16. I don't know how many of these, how much is too expensive. I'm not sure. What I do know is that if you take a look at the way a GPU works, or a CPU and that, for that matter, the fact that they tend to be wide often means that you can figure out a way to do things so that you can get 16 things done at a time if you have the same inputs to them. So for example, if we're going to do the same 16-ray check against a particular incoming primitive, that's probably as cheap as just doing one. You can get that parallelism out of it, and so if you're doing something like ray tracing, it actually behooves you to do 16 primitives at a time if you can. And so, there's a certain degree of leverage we might be able to get there in terms of getting back to something that's more like rasterization in terms of its lane utilization anyway. So maybe that gives us some options too. So this is what I would like to explore. The reason I would like to explore this is because I think the only way we're really going to get better shadowing in there is to start thinking about directional occlusion rather than just thinking about general ambient occlusion, because direction occlusion is the only way to get sort of the knowledge that something on one side of a wall can't collect much information for something on the other side of the wall. Not a very controversial thing to want, but just a difficult thing to get. So if we come back to sort of the more pragmatic side of things here and just say, how are we going to actually implement something like this? Well, the brute force and really straightforward method is to just literally have some way of intersecting our line with our primitives, right? Now, this just comes back to another ray plane intersection, which we sort of talked about before. But what we know is that each of our reflectors is actually in a plane, right? Whether we choose to do a disk or we choose to do a sort of parallelogram or square of some kind in the future, one thing we do know for sure about them is that they are always going to be in a plane. And if something is in a plane, we know we've got ray plane intersection. If we're trying to see where along a ray a particular one of these reflectors is, well, that's pretty easy to do. All we have to do is do ray plane intersection, which we've done before. And one of the things that's really clear about ray plane intersection, right, I can derive it for you. Again, it's very, very straightforward. It's a very simple one to do. If you have an origin point, right, here's P0, and you have a direction normal, we'll call that N. We'll just assume that it's normalized. If I know that I want to hit, well, I guess I shouldn't call that N. Let me call that D for direction, because I'm going to want to call the plane's normal N. If I then have a plane somewhere out here, which has a normal N, right, and a particular origin point here that's described as the distance along here. You know what? I'm picking really bad letters today. I'm going to call this R for ray. How about that? Because this is going to want to be the D value as well there, right? So what we know about this is if we have a plane somewhere in the world described by our standard ND formula, and remember a plane is one of these equations, right? AX plus BY plus CZ plus D equals 0, right? This is an affine plane. This is a linear plane right here, an affine plane plus D. So this is the standard equation for a plane. We've seen it before. If you haven't, you're going to want to use the Handmade Hero episode guide to go back and look at where I talk about planes and how they're described. This right here is just the normal times the incoming point. So this is really just nx times px plus ny times py plus nz times pz plus the d value for the plane equals 0, right? So this is the normal to the plane in here. This is the point we're testing on the plane. This is the d value for the plane, right? Hopefully this is all coming back. I should probably look at the chat right now to see if everyone's like, wait a minute, I totally forgot how planes work. Hopefully that's not true, but maybe it is. Anyway, so we've got this equation for the plane. And really all we want to do here, in fact, I could even use just a straightforward equation for the plane if we want to, just this right here. All we need to know is where does this equation, right, line up with the equation for array. And remember, the equation for array is just going to be, and I could take furthermore the simplification of this P0 point can be subtracted out. So we can make this be 0, 0 just by subtracting away, transforming the plane into the space or the ray even. We can make it even simpler ourselves and just say, look, the ray is just a t value that goes out along the ray. It's just trx, try, trz is just the point, right? That's the point along the ray as we go out along t. So if we walk along this proportional to t, trx, try, trz is just the point that we would end up on, right? Again, this should be all review, so I'm not going into it in too much detail. But point being, if we just want to solve these equations, we're just looking for the equation that solves this for t, and it's a pretty straightforward thing to do, because if you take a look at how it works, we would just substitute this point in to this equation and we're basically done. So for example, if we just substitute in a t rx plus a bt ry plus c t rz plus d equals 0. What you can see here is that the t pulls out pretty straightforward, right? I just end up with t arx plus bry plus crz plus d equals 0. And if I want to solve for this, well, it's pretty straightforward again. I'm solving again for t, which is the length, which is the distance along the ray I've traveled so far. I just get t equals negative d over arx plus bry plus crz, right? And that tells me how far I had to step along the ray to get to the plane, right? So again, it's a very simple substitution. We have an equation that tells us how we're moving along a ray. We have an equation that implicitly tells us whether we're on the plane or not. So we just substitute in the equation for how we moved along the ray into the equation for when we're on the plane, and out comes the answer as to when we would hit that plane. Now you will notice that sometimes we won't hit the plane. How do I know that we sometimes won't hit the plane? Well, first of all, it's pretty obvious if you think about it. If the plane is facing this way and we're pointing that way, well, we're never going to hit it. We're just going to go forever and we're never going to hit it. If we're pointing slightly that way, we would hit it. If we're pointing slightly that way, we would hit it when we go backwards, right? But if we're pointing directly perpendicular to the plane normal, we won't hit it. Hey, big surprise. That's exactly what this says. This is the denominator of an equation. We know that the denominator of an equation can't be 0. That means arx plus bry plus crz cannot be equal to 0 if we want this equation to hold. And so t cannot have any valid value if this were to become 0. When can this become 0? Well, those of you with special eagle-eye vision who have been watching Handmade Hero all the time should know what this equation is. Does anyone know what this equation is? Please tell me someone knows what this equation is. I'm not even going to look at the chat because I really hope that someone knows what this equation is. Hopefully you said that this equation is the inner product or dot product, because that's exactly what it is. It's the x of one thing times the x of another, the y of one thing times the y of the other, the z of one thing times z of another. What are those two things? Well, they're the n and the point, right? So a, b, and c are, like I said at the top, nx, ny, and z, right? And rx, ry, rz are the points of the ray. So if I have the points, the x, y, and z of the normal, the x, y, z of the ray, I'm dot producting them together. What do we know about the dot product? The dot product is length of a, length of b, cosine theta. When can the dot product be 0? Well, only if the lengths of these two things are 0. We know they're both not. Or if the cosine between them is 0. When is the cosine between two vectors 0? It's 0 when they are perpendicular to each other, right? Because the dot product of this and this, cosine between those two angles is 0, because of course, right, we know as it kind of comes up, the cosine starts at 1, comes up, 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 up to 0, right at 90 degrees, which is exactly what we'd be at if they were perpendicular, or negative 90 degrees as well, right? So negative 90 or 90 is going to be 0 in both cases. If it's perpendicular, cosine is 0. What did I just say? We're never going to hit it if we're perpendicular to the normal. Here's the ray direction, here's the normal, dot product them together, they're 0, done deal, right? So effectively, all we're saying here in this equation is just, yes, you will hit the plane eventually. This is when you'll hit the plane. If you happen to pick a direction that's perpendicular to the plane, surprise, surprise, you won't hit it. Shouldn't be shocking. Okay. Anyway, all that stuff is review. You should have had that from earlier in Handmade Hero, so I'm not going to belabor the point. If you haven't, I highly recommend you consult the oracle, whose name is Miblo, and he will, through his episode guide, tell you the place you can learn more about ray plane intersection. But once we have a ray plane intersection, what we can do is we can say, all right, for all of those reflectors, if we're looking at one of these and we want to take a ray that goes out into the world, if we want to figure out where the ray hits things, what we need to do is take those reflectors and we need to figure out when we hit the plane, right, we will know. That will produce a t-value, like I said in the previous equation, that will produce a t-value that tells us when we have hit a plane in the world, right? When we've hit a plane in the world, that tells us we have hit something in the plane of a reflector. It doesn't tell us if we've actually hit the reflector. And in order to tell us whether we've actually hit the reflector, we need a model for the reflector. Now, the way that we've currently been modeling the reflectors is effectively as disks. I don't know that we really want to do that anymore. One of the things about the only reason we picked disks in the first place is because we were using this sort of disk-to-disk measure of size. We can still do that. We can still use the disk as the way of computing how much light is transferred. I don't know if we really want to use that for shadowing. The reason I don't know that we want to use it for shadowing, and we really don't want to use it for transfer either, so we may switch to something better for transfer. The reason you use it for transfer is because it's symmetric and easy to compute, but it tends to undercount our squares, right? So we could either overcount or undercount our squares. I'm not sure which one we want to do, but you could think of either one as being bad specifically for shadowing. If you undercount, then you're going to let more light through than you should. If you overcount, you're going to block out too much light. So it's not clear that you want either of those things. The important part here is just for the shadowing part of this equation, which is what we're talking about now, when we hit a plane that has a reflector on it, right, because that's the test that we can do, we then need to know is, did we hit the reflector itself? In 2D, this is much easier to see. If I, again, look and I say here, let's say I'm casting along this ray out from this reflector. Well, when I hit the plane, I'm going to get this point back, right? And what you can see from the diagram is that point doesn't actually coincide with the reflector at all. So technically that's not a hit. We would say that that ray misses the reflector. It doesn't hit the reflector, right? So again, we have a number of ways we could do this. When we produce that point, what we could do is we could use, again, let's say we stick with the disk formation for now, again, it does provide some nice simplification. If we have the disk formation, what we can do is just say, well, what's the distance between those 2 points? If the distance is less than the radius, well, then I guess we hit it. We're inside. If the distance isn't less than the radius, we didn't, right? So again, all we're saying here is there's a nice implicit function that will tell us whether or not we're inside the disk or not inside the disk. That's got some nice attractiveness to it. Why does it have so much attraction to it? Well, A, it's just a very simple x squared plus y squared less than r squared kind of a situation, so that's kind of nice. So we've got a nice way of testing whether we're inside it. The other thing that's nice about it is it composes really well if we actually did want to do cone tracing of some kind. Now, we can't do exact cone tracing here in the cheap way, but we could do some fairly free cone tracing that's sort of approximate. How would we do that? Well, if you think about this as tracing out a cone, what's pretty easy to do here? Well, we've got a t-value that tells us how far out we've gone. That t-value can be directly proportional to the cone size, right? So when we get the t-value back that says, here's how far you went along the ray to get to the plane. When you go that far along and you get to the plane and you're there, you then have a t-value you can use to plug in to say, what's the size of my cone at that point, right? Because I would know how big the cone would be proportional to t. That's a pretty easy thing to set up, right? We can just say how wide our cone is, and then we can compute, just based on similar triangles, how wide the cone would be at that plane. Is that correct? Not exactly, because in the plane, that plane may be very, maybe kind of oblique, right? The angle might be kind of steep to it. So it's hard to say how you really want to do it. You may want to take that angle into effect, by dot producting these two together, which you already have to do for the plane equation anyway, and project the cone distance. But regardless of which you do, you can still end up with a radius value that's a complementary radius value to your disk radius. So what you end up with, right, if I shoot out from here, and here's my other plane, I hit this plane, I know I've got a reflector out here, I know that reflector has a radius, we'll call that radius of reflector, I know that the cone also has a radius, right? So I can also compute a span here on the actual plane that is sort of a radius of the cone, right? And the radius of the cone can tell me if I overlap as well. So what I can do is say if the distance between these points is less than the radius of the reflector plus the radius of the cone, then they've overlapped, right? And furthermore, I could see how much overlap there was by comparing the distance to that. So it does set me up for doing some cone tracing as well. It's not as easy as I made it sound because, if you want to take into account this angle, you have to actually project the cone onto the line, which takes more work because it's not symmetric anymore. You have to come up with sort of the new span in that way. So it's a little bit tougher to project onto it. And furthermore, if you're doing it in 3D, it becomes an ellipse, right? Because a conic cut by a plane is an ellipse of some kind. So it gets more complicated than that as well. And so I guess I would say, it's not like really free, but you could cheese it out. Like you could do something where you just kind of roughly attenuate it, and you treat it still as a cone, not as an ellipse, but as a truncated cone always, and you just pick the cone sort of size to roughly match the angle of the plane. There's some hand waving there we can do, is my point. So yeah, that's an option, right? It's something we could think about. And I do think the cone tracing might be interesting to a certain degree. I'm not sure how good of a results it would really give us, but it's something to think about as we go forward. All right. So, I need to blow my nose. Where do we go from here? So what I think we want to do here is, pick a particular one of our reflectors, right? And what I think we want to do is pick one of our reflectors and do this computation for it. Now, why do I think we want to pick one of our reflectors? Well, if we pick all of our reflectors to do this for, we're just going to end up with a nightmare. First of all, we're going to have to optimize the thing well enough to make sure that it runs fast enough so that we can see it, operating on 500 reflectors. Again, on the CPU, single-threaded, that's not great. Single-threaded, non-SIMD, that's not great. And I don't want to deal with that right now. Second, we're not going to be able to see what the heck is going on. What we want to be able to do is draw some lines or something. We want to be able to draw some debug information here so that we can have some idea of whether this thing is working or not and whether or not we got any bugs. We're about to introduce a bunch of weird like ray intersection sort of stuff here, and we want to make sure that we've got it right. If we can't focus on one reflector and see is it actually doing the occlusion that we think it should be doing, we're going to be, I think, in a world of hurt. So I think what we want to try doing here is to just go, okay, let's try taking one of these reflectors. Let's do the one behind the wall, for example. Let's see whether we can get that one computing 16 rays out from it, 4 rays out. Well, first we'll start with 1. And we'll see if we can get that behaving properly. Once we have that behaving properly, then we can sort of take that and move that into the space of doing all of them. And we don't really care how fast it runs because, again, we're just on the CPU. We just want to see if it produces pleasant results. So we'll try to get it running as fast as we can in terms of seeing, how it does. And then we'll go on from there. And that will give us the information we need as to whether or not this is a fruitful thing to pursue or not, and whether or not we can produce a relatively artifact-free version of it. And off we go. So what I'm going to propose at the start is that, so anyone who's not on board should make their opinions known. Unfortunately, the way you would make your opinions known is by putting them into the chat. I don't read the chat during the stream, so it is effectively a democracy where no one listens to you, which is, we have a term for that. It's called democracy. So basically what we want to do here is have everyone cast a vote to make them feel like they're having input in the situation, while the effective aristocracy just makes the decisions for you, just like every government in the world right now. I am that government, and you are being oppressed. So there you go. Welcome to the real world. So off we go. What I need to do now is figure out which one of these I'm going to do. I think the easiest way to figure out one of these is to just pick a sort of debug value we can put in, and we'll adjust that debug value to pick a particular reflector that is like the closest reflector to that point, let's say. And that will allow us to pull one out effectively. Say this is the one that's going to be the reflector that gets chosen. So we'll call this like refl pick or something. And why am I doing it this way instead of a quad index? Remember, this is actually coming from the renderer. So all of this information is still coming from the renderer. We haven't cheated at all here. We're using the full pipeline effectively. We've just asserted ourselves in, and we're looking at all of the things that are coming in and doing a lighting sort of debug test on those things. What that means is they're not coming in any particular order, right? The game frame to frame sends us totally different orderings for the quads. Even if they're the same set of quads, it can send them in a completely different order. So picking a particular quad by index isn't going to help us here. What I want to do is pick a particular quad by world space location, because that will be relatively stable frame to frame, at least for our purposes. So what I want to do is make a refl pick value here that basically allows me to say for a particular placement, like let's say 0, -2, maybe I'll say actually 0.5, or rather, I want the 0.5 on the Z. So for something that's like, actually 2, something that's 2 up and 0.5 off the ground, I'm trying to pick something kind of over in the wall area. It's probably more like 4 up. I don't really know what the coordinates of that thing are. I'm going to start with that, and what I'm going to do is every time we go over this, I'm just going to have a like close pick value, and I'm going to start that at maximum. What I'm going to do is I'm going to take the distance from just an arbitrary sort of location on this thing. We're already picking sort of a center point, so I'm just going to say let's look at the center point of this thing, and I want the length squared of the element. I'm gonna call this close pick squared. So it's plus close pick index close pick dist squared. So what I want to do here is I want to take a this pick distance squared. I want to take the length from the element to that pick point. And what I want to do is I want to see if this one is the best. So here's the this pick distance squared. What I want to see is if the best one, this is the standard format for this loop. You see me do it many times. Every time through the loop, we're just going to compare our current distance to see if it's closer than the closest one we found so far. So if the close pick distance squared is greater than this one, then we'll use it, right? And our close pick index becomes whatever one we're on. So that lets us know which one of these it is. What I'm going to do is after I find that out, I now have a close pick index value, assuming I didn't mess it up. I'm going to have a close pick distance value that will tell me which one of these quads was as close as the closest one to that input point that I gave. When we do the future passes, what I'll do is when we go to render that particular reflector, what I want to do is I want to highlight it somehow. So you can kind of see there's our lighting equation. Here's where we copy it in. What I'm going to do here is say, oh, okay, let's actually hijack that process of coloring it. In the case where the quad index happens to be the one that we're picking out, let's go ahead and set the front emit to some very obvious value, like bright yellow. My favorite picking value. Looks like that close pick index, oops, I put it in the wrong place. There we go. I don't know what I just hit. I must have hit some kind of search all of a sudden. Anyway, so if I run this now, what I'm hoping to see is that if I view the reflectors, I should probably turn this. In fact, let me just go ahead and turn this on permanently because I'm going to want it on all the time. There we go. Oops. So what I want to do here is I want to figure out a way to get one of these saucy folks to highlight. So what you can see here is we do have a reflector that's highlighting. It's this one here, right there. And so it's almost in the right place. It's not quite back far enough. It's not quite up high enough. So all I'm going to do here is I'm just going to change that value to be up higher and back further, right? And so hopefully we can pick, there we go. And so now we've picked, one of these squares. Maybe I want one of the ground tiles here, let's say, might be a better way to go, let's say, as well. I don't know which one of these would be best. I mean, another one we could do is one of these, but let's do a ground tile. Let's do a ground tile so that we can see that it can't reach the light, for example, because it hits one of these or whatever. All right. So if I want to do the ground tile, just pull it back a little bit, probably maybe 6.0, let's say. Let's see if that's right. Not quite enough to switch it yet. 5.0. And we can move it down a little bit. All right, so now we're picking that one right there. I guess I should probably have drawn this point, but I haven't drawn the point yet. So we're almost to the one that I wanted. Let's pull it back slightly more, and let's move it up slightly more and see if I can't pick that one. Okay. So now we've got a weird little debug procedural way to isolate a reflector and keep it stable across runs so that we'll just run it and it'll pick that one automatically. We don't have to like pick it with the mouse or doodle around with it or anything like that. So now we've got a particular reflector that we can pick there. And what we can do is send that one's lighting through a different path, right? So we can still use everyone else going through the old kind of crappy lighting path, but when this one comes up, it can do some kind of nutso situation, right? So we know that that one's being highlighted now. What we can do is get rid of that highlight because we don't need to see it anymore, and we want to actually just see the color that it actually shows, obviously. So that's good. So now we look at this and we can see that that reflector is getting, treated exactly like everyone else, even though we've got, these light sources that are right there, being blocked by the giant wall. It still gets pretty much direct contribution, just like it would if it was on the other side of the wall. And that's the thing that we want to start taking into account. So now if we want to, we can, again, isolate that that fellow here. When we come through to do the compute lighting, you can see when we sort of have our iterations, we go through the destination. I don't know why total photons received is still sitting there because we don't do that anymore. But anyway, when we come through here and we're doing our computation, I can just pick that one out and do a completely different lighting pass on that particular individual. And what I can do, if I want to here, is I can set it, again, do exactly the same thing as I did to verify. Let me see if this is actually, how is this? Let's put that. So I actually want this as well in the else clause. There we go. So in order to verify that this is actually doing what I want, what I can also do is say, well, the accumulation here, the depth visibility, we don't care about, but this is what's going to get set to the new color value for this tile. Let me set it to yellow here as well. Is that this? Is it a V3 or a V4? Yeah. So what I can do here is say, all right, if the destination index equals the one that I'm trying to do the special lighting on, then what we'll do is do a special lighting path. For right now, we'll just set it to yellow. Again, this should show up as the same highlighted square, right? And it does. So that's good. That's exactly what we want. Although I think that actually, would that mean that everyone else would get lit by a little bit of yellow, in theory? Should be. It doesn't seem to be, though. Anyway, ignoring that fact. So once we've got that, right, I'm wondering why, I wonder why that doesn't put any yellow light into the scene. Something weird is happening there. Wouldn't you say? I mean, correct me if I'm wrong, but if I'm setting this accumulator value to be bright yellow, then on this pass, each lighting pass, it will take the front emission color, which is the thing that pulled in for lighting for, as using it as a source from then on. It will take and use that as, as effectively an emitted yellow light, or it should, anyway, I would argue. But it doesn't appear to be. I mean, what happens if I just crank that value to an absurdly high amount? I mean, I should see something, right? Okay. So it's really just a question of power. And we don't get very much bleed, I guess, from one of those if it's just one, if it's just set to 1. You can see how much fun this lighting is going to be when we get it all nice. Like, it's so cool to have an environment where you can have like multiple light sources and they sort of create this nice sense of space, right? Like, you can see already how this is going to be fun. If you have a game and it's got, a little fire back there or something in it, and, you kind of got this sort of nice space being created by the different pools of light. Especially so if we start getting it, again, so it properly doesn't transmit any light to surfaces that are being shadowed or whatever. Anyway. So we know we're picking the right one in this routine. What we now need to do is implement this loop differently, right? So if we imagine here we've got this source index sorry, I'm just thinking. So anyway, if we assume we got this source index, and we're going to loop over all of these, and we know we don't want to test against ourselves, obviously, so this equation still more or less does what we expect it to do, right? So we want this to basically be the same. We're going to take the light that we know is incoming, we're going to take the vector to the light, we're going to see it's got to be in front of us, basically, and it's got to be, some reasonable distance away. It can't be 0, it can't be right up against us. And then what we're going to do is take the to light. This is that normalization. So to light is effectively the ray that we would be searching along. And what we also would find at this point is that we can take, again, that plane equation. We know what that is as well because we know what the source normal is. So I can actually compute this fairly directly. So if we want to look at that inner product, and again, this is inner product we're already doing for lighting. You can see right here we've got, well, no, maybe it's not. I don't know if we ever do this one for lighting, actually, I guess. But if we were to take a look at what the sort of the inner product is with the direction we're searching along, oh, right, no, so, okay, I take it back. Because that's the one to the light source. That's not the direction the ray we're searching along. So I take it back. I take it all back. I forgot we need another thing in here because we're not just doing one search. We're not just searching along our main normal. We're actually going to search along potentially more than one of those, right? So if I say that in here we're going to have like a ray index equals 0, ray index is less than however many rays there are. So what I want to do here is say, okay, let's suppose that I just have a bank of rays that I'm going to cast along. So I just have multiple of these, right? At first, I'm just going to try casting along, I guess, a single one of them probably. So we'll just say, you know, there's just going to be one ray. And maybe that ray is the ray that is the reflector ray. So we will actually treat it the same. So we'll just say, I've got the reflector that I'm computing. I'll just cast out straight out from it, because we know we're probably going to do that one. But then we probably want to add a few more in here that are going to capture the light from sort of other directions as well. So we'll start with that one. We're going to loop over the rays here. We're going to say for each ray, we need to figure out sort of the normalized version. We're assuming this ray is normalized. So assuming that the light is not too close to us, what we're going to do here is sort of collide against the light itself. So I take it back. We don't probably need this so much. If we take a look at that ray value, we can say, all right, the ray that we're shooting along is going to be ray's ray index. We want to now figure out whether that ray and whether that ray will ever intersect the light, the plane of the source. And so the way that we would do that is, again, by the inner product, like I talked about, take the inner product of the ray and the source normal. That gives us an idea of ray source n. That gives us an idea of whether or not there's any chance of hitting. What we want to do is avoid anything that's too like oblique to us. So if something is really on the edge, like we really only want things that are going to be in the reasonable hemisphere around this point. So we want to look to make sure that there's a reasonable amount of approach to this. So we look and see this. Again, this is that cosine term here that I talked about back here. That's this term right here. So we're basically saying, okay, we're casting out from a reflector. We have a plane. So this is our ray. This here is the source n. We're taking the inner product of these two things, and we want to see that they have a reasonable approach. Now, I guess now that I think about it, though, we want things pointing in the opposite direction to us. I'm glad I just drew that diagram. So really, we want this to be negative source n, if you will. We want it to be pointing back towards us, not away from us. And so we want to negate that sense, right? Because we are doing the diagram this way. We want the normals pointing towards us. So we want the dot product, if we're looking for it to be positive, we actually want it to be kind of coming out this way here, right? The other way we could do that is to just invert the sense of this, right? We could instead say, well, it goes from 0 to -1 there or something like that, but it seems easier to just invert it there. I don't know, 6 1/2 doesn't have the other, right? Similarly speaking, I suppose you could just negate it on the way out, or you can just negate it here if you want to. It's going to be the same either way, right? So you can just, the negative will distribute over the dot product. So anyway, this is the value that we want to know in terms of how aligned they are. Again, if they're 0, 0, they're perpendicular. If they're 1, they're directly facing each other. And everywhere in between is OK with us. We want to compute our ray t value. So that value that I said before, which we had computed over here, this stuff, where is the actual, here it is. So it's the -d arx bry crz. So what we want to do there is we can compute it almost directly, but not quite, because we don't actually know what the d value is, but we can easily find out what the d value is fairly cheaply. I'll show you how to do that in a second. So anyway, if we want to do the t-ray computation, what we do is we say, all right, we've got ARX, BRY, CRZ. Again, the A, B, and C are just the normal are just that source normal. And again, we want to probably use the same source normal that we were using. We need to use the same one that we used for the inner product. So since we're negating the inner product here, again, we need to use the same one in both cases. So, you know, what we could do is say ray source n. We could leave it this way, again, and do something like that, which maybe we want to do so that the source n is still used directly. Then we can use the source n directly here for the inner product. So we can say source n. Well, actually, I guess we just did the inner product, so it's ray source n. This is that inner product of ray source n, right? Nx Rx, Ny Ry, Nz Rz, and that negative d needs to be on the top. So the problem here is, what is negative d, right? We need some way of computing that negative d. So in order to compute d, what we have here is d is supposed to be the AARX BRY plus CRZ plus d equals 0 for the plane equation, right? That's what we're supposed to get. And we wanted this centered around the ray, so again, dest p has, the origin of the ray, has to be where that's centered around. Well, we know that dest p, you know, the location of the source, producing a point on the source relative to the destination is pretty easy. We know that the relative source p could just be found by subtracting the dest p, you know, the source p, subtracting away the destination p from there. That produces for us a vector that goes from the destination to the source pretty easily. Where is my diagram of that, what we were just drawing? Didn't we have... Thought I was drawing something else here. Oh, okay, I drew it right here, I guess, for some reason. All right. We can produce this value pretty easily, right? Because this is our destination reflector, this is our source reflector out here. We can produce this arrow pretty trivially because it's just the source position minus the dest position. Problem is, we want the d value of the plane. So how do we get the d value of the plane? Well, we can actually just reverse solve the equation to find that out, right? We know that we've got, you know, nx px plus ny py plus nz pz plus d equals 0. We want to solve for z. We know all of these things, right? So all we have to do is just put them on the other side and we're done, right? In terms of figuring out what the d value is. The d value is just going to be negative nx px, negative ny py, negative nz pz. What is that? It's just the negative dot product, right, of n transpose p. That's it. So we can do that very simply by just saying negative inner product of n and p, right? So that gives us that d value that we wanted, and now we have our intersection point, right? Very, very simple, nothing to it. So there's our test for how close our intersection is. What we want to do now is say, well, okay, I needed a bigger one. I'm out. What I want to say now is like, okay, if I've got that, I need to have some understanding of whether or not I've actually hit it. And like I said, we can do that with a pretty simple check. Again, we can produce the ray point essentially by taking our starting point and adding the ray times the distance along it, right? If I start at where we started, where the ray origin is, if I add however far we went for the intersection times the ray, I should step out to where it is. Now I've got my point at the intersection place. I can then take the distance and figure out whether or not I intersect. So the intersection is just going to be, ray, and I can see here, dist squared is just going to be ray p minus source p. Well, actually, relative source p. Got to keep them in the same space, right? So I know if I take the ray, the location where the ray is going to be. Oh, and actually, I guess I don't need to do that, right? If I take the location where the ray is going to be relative to the the destination P, if I take where I would actually hit the plane, I subtract away where the source is in this space, I end up with a distance squared, right? And then I can say whether it intersects by just saying if the distance squared is less than the square of the source radius, right? So if the distance away of the point, again, I'm just doing exactly the thing I said I was going to do. If I intersect a plane, let's say here's where the reflector is. This is the source reflector. Here's the destination reflector. I come out here, I find my intersection point, and now I say, how far away am I from here to here? Right? How far away am I? I'm going to get a value out. All I want to do is compare it to this radius. If it's more than that radius, I didn't intersect. If it's less than, I did. That's all I have to do, right? So I take the length squared, and I can compare two squares just the same as I could compare the non-squared versions. Doesn't change the direction of the comparison at all. So I can just say if the length squared, so this just avoids the square root. If the length squared of these is less than a radius, I intersected, otherwise I didn't. That's all there is to it, right? And in fact, I can just put that inside here. I don't even really need to look at it. Right? So there you go. So if I intersected, then I know that I've got a new intersection value, and off we go. So that's effectively the code for doing the shadowing along the ray. And what I can do now is just say that outputs a value per source that determines whether or not I actually want to compute the lighting. What I could do is still use the exact same lighting transfer that we're using before, just by nesting these down. So what I could do is say, all right, let's actually just make this whole thing actually just be a preamble that happens, right? So what I can do here is say, all right, let's just get this whole thing going. Right? And all I'm going to do here is, what do I have to do? So this is the des index here. Did I keep that in the right line? Des-accum, yeah. So all I have to do here is just say, all right, for each of the sources, I'm looping over. I got rid of the other sort of version of the loop. So instead of this here, I'm just going to say, for each of the sources, I actually wanted rid of this stuff, and say for every source, I'm going to do exactly what I was doing before, but if it happens to be this one special one I was trying to look at specifically, what I'm going to do is compute a shadowing value for this source by using my ray information, right? That's all it was going to do. Now, I guess there is a problem here, which is I kind of do have to do it beforehand, because in order to do this, I have to compute the shadowing information before going further, I guess. So this is going to be a little bit tricky, but so if you take a look at what happens here, normally we're summing up all of the accumulators, right? And so what I'd rather do here is, I guess what I would rather do here, here's the way we can actually test this a little bit more carefully. Let's actually put it in here. So after I do the light contribution, before I do the accumulation, what I'm going to do is say if it's the normal case where we're not the special reflector that we've picked out, then we just do the summation as normal. Otherwise, what we're going to do is we're only going to use, let's say, the light that is the closest one that we hit, just for starters. So the way I'm going to do that is I'm going to say, all right, let's introduce a value which is closest hit. I'm going to call that value F32 max here. So it starts out being nothing. When we come through here, I'm going to say, all right, we test against our rays, and you know what? I'm going to have the closest hit. I'm going to put this rays definition up at the top as well. So I'm going to say we've got, here are our rays, and we've got our closest hits. Our closest hit is also an array, an array, which is one for every ray, right? So when we come down here, what we can say is for this particular array, if this was a hit, first of all, we can say before we do any other checking, we can just say if t-ray is less than closest hit or something like this. We can do that here before we bother computing whether or not we actually hit the thing, because we don't need to bother checking this if we aren't even going to be the closest hit yet. But anyway, what we can do is say, all right, we've got a particular ray. I want to see whether or not it's the closest hit or not. So I'm just going to say for this ray index, was this ray closer than the closest thing I've already evaluated? If it's not, then I'm just going to ignore it. If it is, then I'm going to go through and see if I actually hit. If I did hit, I'm going to make this be the new closest hit. So this just gives me a way of saying which light source is the closest along the ray. And what I'm going to do is I'm going to set the accumulation C to just be whatever the result is just along just that one ray, right? So that's the end of it, right? Now what I'm assuming will happen here, other than having to fix compile errors, what I'm assuming happening here is this should make our square be black, probably, if we did everything right, which we probably didn't. But, oh well, it is black. Of course, there's other ways it could be black that aren't, that don't have anything to do with that. The reason I say that is because if you think about what we just told it to do, we said only use any thing that's directly above, it's doing a cast straight out the top. Only do something that's straight out the top. Now, we could see if we're working at all by moving over here and seeing if we ever get, excuse me, right on top of it. And it looks like it does work if we do that, right? If we're right on top of it, you can kind of see that we do get a, well, actually, no, but you know what would happen there is, if we're right on top of it, what's happening there is we're actually picking a different closest point. Let me get rid of the hero sprite again, because that's just creating, again, too much of a problem for our test case. All right. So let's try that one more time. If I go ahead and move up here, let's see whether we can ever get. So it doesn't look like we're actually able to get that to hit, even though we should probably be hitting it as we pass through there. So that would suggest to me that it's not really working properly. Now, one thing I can do, let me just make it a little bit easier for us here, which is if I go to handmade world mode, I thought we had a way to add the lighting in here. Oops, that's not world mode, that's world mode. Let's push light, that's what it is. So when we push the light on here, let's give it a much larger radius. So now you can kind of see that we've got, if I come from the perspective here, so now we know that if we debug this routine, we should allow, the ray should be able to hit this emitter here, and it should actually work, right? So now we should be able to get sort of that, that information going forward. So that's good, right? That's what we want. All right, so what we should see here is we should be able to go back to our code. We should be able to debug it now so that we actually do hit the light that's coming off. In fact, let me go ahead and just actually step through it there because we should have, in this case, an intersection here for the light, and it should be able to transfer that, that light that's above it, should be able to get a hit on it. So let's go ahead and see, do I have a way to get into render? Nope. Okay. So let's go ahead and see what happens if I go ahead and step into this. And what I'm going to do here, don't try this at home. I don't actually know if it will work. Is I'm going to actually try on the fly getting this to go into debug mode. So this is a release build, and I'm just going to try compiling in debug mode with hot code reloading, which apparently just worked, which is awesome. And then I'm going to step in here. So effectively what I'm trying to do here is figure out why we're never getting inside here, or to see whether or not we're ever getting inside here. So we are we ever getting inside here? We are. So it looks like we are making it all the way into, in fact, it looks like we are actually getting a hit. But there is our problem. So, or at least one of our problems. So one of the things I neglected to do here is clamp the ray to, it's allowing hits that are behind it, right? This T-ray value is going to cast out in both directions effectively. There's nothing that prevents it from shooting backwards. So T-ray can come out negative, and it's always, any negative values are going to be less than any values that are positive, because negative is always less than positive. So it's always going to pick something behind us, which is emphatically not what I wanted it to do. So what we really want to do here is say if T-ray is greater than 0 and less than the closest hit, right? That's actually what we wanted it to do. That's the more fruitful approach. So let's try that and go from there. All right. So what we can do now is rerun and start debugging this new, not so busted version. All right. So what we see now actually is it appears to be working more correctly. You can see as I move over the top of it, I actually do, once it moves into sight, I actually do hit it, and when it moves out, I'm no longer hitting it, right? So that's actually quite nice. That's actually exactly what I wanted to have happen. So now that's perfect, because what that means is that if there was something in between the two of these two things, we would actually get the shadowing happening, which is exactly what I wanted. And off we go. So we could run this on everybody. Of course, it's expensive, but we could run this on everybody. In fact, let's go ahead and do that just temporarily to see how slow it actually is. The problem is we're only casting out one ray right now. When we start to cast out more rays, it'll become a lot more expensive and probably won't work, but I can obviously do that fairly straightforward. All I have to do is, as we go, I just get rid of that if statement, right? Well, in order to do that, I'd have to get rid of the bottom if as well. You know what? Let's just do it this way. Let's just say if 1, so it will always pick that path in all cases. So this is going to be a lot slower now, presumably. And what you can see here is it's also got, obviously, the problem of, since it's only casting out in exactly one direction, almost no lights ever hit any other surfaces, right? And this is exactly why I say you need to have a lot of different directions so that you can cast out and find other sources that you want to hit. So if this is actually working properly, we don't really know it's working entirely properly yet because we haven't really done much testing other than to see that it sort of looks like it's working. If we now start casting out in different directions, that would give us something potentially usable. This raise value is obviously kind of a constant thing that we can do. Let's go ahead and cast out some other rays, right? Just some other rays in other directions, right? So if we want to cast out rays in other directions, we need some way of figuring out some other directions to test, right? And the problem with this is that's easier said than done in our particular circumstance, because we don't really have very much information at this stage to figure out where that should actually go. And you know what I'll do here is I'll just put a bunch of these in there. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, there we go. Don't ask me how I ended up picking exactly 16 there. I don't know. But what I want to do here is say, okay, for each of these rays, I want to have some other possible rays to cast out. And what I'm going to do is I'm going to do the stupidest possible thing. This is really bad. Don't do this at home. And we'll definitely need something better later. But what I want to do is I'm just going to create 8 rays here for the time being, just by perturbing each of these by some value, right? So I'm just going to perturb each of these by something. Basically, pretty random, right? Nothing particularly smart here. I'm just picking random rays. Oh, never mind. This isn't constant. What am I talking about? This is per destination. Yeah. I'm just picking random rays, and I'm not picking them in any sort of smart way. I'm kind of surprised at how fast that actually was running. But what you can see now is that we now have more chance of picking things up, right? Because each of the rays that we cast out effectively has, it's got 8 chances of being in the direction that will actually hit the light source. And that's great, but again, not good enough. And if I went and picked those rays better, we would get more intersection, certainly. But what you're seeing here is specifically the sort of thing I was talking about before, where I was like, casting out rays by themselves probably isn't going to cut it. The number of rays you would have to send out is just going to be too high. And granted, when we start doing this in a multi-resolution fashion, which we're going to do eventually, it will be better, certainly, but it won't still probably be good enough. So that's why I was thinking what we probably want to do here is make something that's going to be a little bit more cone-based so that it can pick up more hits. So if we want to ray trace something that's going to be a little more cone-based, what I can do first of all is let's switch back to this so I can verify that our cone-based tracing is actually doing something. What I can do there is expand the radius of the cone as we go out in a really, like I said, very cheap and cheesy way. And so what I'm going to do there is say, okay, let's suppose that when you cast the ray out, as it gets further out, it gets wider. So this distance here, where we look at the distance squared is less than the square of the source r, what we actually want to do there is take a look at if it's actually the source r plus plus whatever our cone radius is, right? And our cone radius in this case is just going to be proportional to t ray. T ray is the thing that kind of goes out, and what we can say is for every certain distance that it goes out, it gets a certain distance wider. Now, what we could say is that it could be exactly even at this point. It could be that for every unit it goes out, it gets 1 unit wide. That might be a little bit too wide, but for now we can sort of just say that's what that is, right? And so now what we should see again is a much smoother, like and you can actually see it here quite specifically. You can see that you get a much wider pickup for all of these lights, and so even though now we're just casting 1 ray, you get quite a bit bigger pickup if you're casting out a cone because it makes it a lot easier for them to be seen. Now the problem that we get, well, I do think we might have a bug in the cast though, because it doesn't make a lot of sense as to why that would be the specific area that this would pick up. If this were casting out a cone, it should pick up this as it gets further away. It should be picking it up right now, in fact. Oh, well, you know what? But it's making other things are being closer in the cone. So that's actually not that. That's actually not that unusual. Yeah, that's fine. Yeah, as you can see, if we make it a wider cone, we can pick up more things. The problem with this is if we only take the closest hit, that means that our cone is not going to be doing a very sensible thing for us in terms of sampling. So what's going to happen here, right? Imagine if we're tracing out a cone in this way, right? then our problem that we're going to get is that something that's in the cone like this, maybe there's a giant reflector right here that's what we should mostly be picking up. Some little thing that's in the cone right here, that's going to register as the first hit, and we're not going to get any contribution from this at all. And so what we want to probably do there is say, let's take a look at when we hit something, how close it is. We kind of want to know something about how these values should be composited together, right? And so we get into sort of the same problem we were having with the depth peels before. It's almost, we kind of need to know, for the cone radius, we kind of want to know how much of the cone you're intersecting with, and how much of the cone you're intersecting with should sort of make you have more or less contribution to the thing that we're, to the lighting solution, right? And so things that only intersect the cone a little bit, we don't want them to block out things that are very heavily in the cone. So yeah, again, we get back to that sort of same problem. Now, if we wanted to do something creative there, like I said, there are things we can kind of do. If we want to, we can try to make these be a little bit more sensible in terms of how they're picking up what's left in the cone. For example, what we could do is, again, pick sort of that multi-sampling, take sort of that multi-sampling approach in the cone. We could say something like the overlap amount is going to give us some indication of what's happening. We could try to sort along the t-values. I don't think that would be particularly a good idea necessarily, though. So again, yeah, I'm not sure. I'm just really not sure what we want to do once we've produced that value. Certainly what we could do is take how much in the cone you are, and we could say something like, we could have some heuristic that we use that's like how much in the cone you are versus how far away you were, or something like this. I don't know that's ever going to produce a particularly good value. So here's what I'm going to say. I'm gonna step back from this slightly because we're coming up on the end of the stream. So I'm going to leave this for now. We're going to think about that a little bit more. But I'm going to leave that for now. And what I'm going to do is I'm going to do something really ridiculous. Because why not? And what I'm going to do here is I'm going to say, all right, let's suppose that we take our bank of rays here. And I'm going to do this in a very different way. So what I'm going to do instead is I'm going to say, let's take some ridiculous number of rays here, because we can. Let's take some ridiculous number of rays, and let's just generate rays at the start that, let's generate 32 of these guys that aren't based on any normal yet. So what I'm going to do is I'm going to say for, 1 to however many of these I want to do. And closest hit, I guess we can also do a ray count rays. So this will initialize to any number of rays that we want for the time being. So what we're going to do is we're going to start by saying, all right, each of these rays is going to be equal to a random value for now, right? So what I'm going to say is we're going to do a normalizer 0, and we're going to pick literally a bunch of random values. Where's our random? So we want a random bilateral. Like so. We want a random bilateral on a random series. So here's our random series. And we just want to take basically a random direction, not a particularly good random direction, by the way. We're going to take a random direction. We're going to take 32 of these rays here. We're going to generate 32 random rays, sort of cover a sphere in them. When we come through here, I'm just going to loop over them. I'm just going to skip any ray that doesn't point out in the direction of whatever the element is. So what I'm going to say is if the inner product of the ray and the destination normal is greater than 0, we'll use it. If it's not, we won't. So now I'm just kind of blooming out along along a bunch of different directions here, and it's going to be slow, right? It's going to be very slow because we've got too many rays, if that makes sense. And I just want to see how many of these it would take to do anything interesting. It looks to me like it's not still enough. Let's see what we have to crank this number to. I'm just curious. So it's still not really able to pick up what I would expect. I wonder if I've got, I may have some, this is not a very good test because I may just have some really bad bugs. At 256, it should be pretty much picking up most things and just be incredibly slow, right? Yeah, so if I look at that, it's still, so I think we may have some bugs in there. At 256, it should be roughly good. Although, to be fair, these things are not as big as they probably should be. Because remember, we're sort of subsampling. I do wonder if maybe we did something where we overfill a little bit. Like, so we've got kind of this minimum span thing here. If we did something where we actually tried to overfill that a little bit, if we did something more like this, I'm wondering if that is more representative as well, just to get the reflectors so that they cover the scene better, right? You know, eventually that does seem like it's kind of working maybe a little better, but honestly still not really. So I think we still got some bugs in there. Let's take a look. How much time do we have? 7 minutes? Not really, no. So let me take a look. I think we've got some bugs in there at the moment, unfortunately. Because that doesn't seem quite right to me. So I would like to have a little bit more information about what's going on here and why. So presumably if I set this down again to some relatively low number, it should be plenty fast. And of course it is. But again, you're only getting rays in certain directions there. And in theory, 16 rays should have been roughly the same speed as before, because that should be the same as casting 8 rays, because some of those rays, you know, half of those rays wouldn't be used, right? But it doesn't look like that's really the case necessarily. So I'm wondering kind of why that's why that's true. Maybe just because I don't know why source is getting picked up twice there. That doesn't make sense. There we go. So that's a little odd. I guess there's just a few more inner products, and that does seem maybe like a problem, but still. So yeah, what I'd like to do is I'd like to look at those. Let's take a second to just look at what those rays actually are. Is there a reason that none of my windows ever stay open, by the way? Like, what do I have to do to make it so it doesn't clear all my windows? I have no idea. What I'd like to do is I'd like to see what those rays are, right? I'd like to just see, let me make sure that they're picking sensible rays. I don't know if I can, I might have to compile in debug mode to see it. No, it doesn't look that way. That doesn't look great. Let's go ahead and step in there, shall we? I'm gonna that may have just been an artifact of me getting the wrong breakpoint. Okay, yeah, this looks much nicer. So yeah, that seems reasonable. And again, I think if we step in, we should see that when we go to test these rays, we only test about half of them. Which you can see happening here. And that looks about right. Right? Yeah. So if I am to do, yeah, like I said, kind of a lower number of those, and I don't know, like, I mean, I could do a lower number of rays and conical. This is something I think we'll just leave till next weekend to think a little bit more about. But I'm just kind of playing around with it a little bit here. So maybe this grows at a rate of like 2 meters, 0.25 meters per meter gone. So there's the cones are narrower. And we'll take a look here just to see. So if the distance squared is less than the source R and the cone R, so this is the cone version of that. And yeah, it just looks buggy, because, you know, the one that's underneath it, I guess it could be never shooting out anything in that direction. Maybe we just need to be more sensible about picking the directions. And that's fine too. I guess we can try that really quick. If we were going to pick directions a little bit better, how would we do that? Obviously, we don't really want to do the random stuff quite yet. So, oops. So if we were going to do something more like that, we'd just do we just do something that was based off of the destination n. So probably here we'd just say dest n. What we'd want to do here is take the destination normal and offset it by certain amounts. Those amounts want to probably be in the plane of the... they want to be sort of distributed in that hemisphere relatively well. That's actually surprisingly hard thing to do. There's actually quite a few people who've written things about how do I quickly generate you know, given a normal, how do I quickly generate good directions to search along? And we should probably take a look at some of those. I don't recall all of them at the moment. But basically what we want to do is something here that would give us the ability to base our search directions off of the normal, right? And probably here, I guess this is probably sufficient. It's still not great. It's not good, let alone great, but it might be good enough for us to test here. So here's one that has a more reasonable search direction. It looks like the speed of this is pretty bad in terms of, I don't know if it's because of the number that there are. I will say that this check can go away because we're now pretty much exclusively producing ones that are going to go in that direction. We could also only do this check if the resulting light was actually going to be seen as well, because right now we're not doing that either. But yeah, that's a separate issue. So let's try that again. And one thing you can kind of see here, although it's still not really very good solution yet, one thing you can kind of see though is we are getting a real solution now. Like you can see that as I move around the wall, I'm lighting up what's behind the wall only when the light source is actually propagating. And so that's kind of nice, right? That's a lot more usable of a solution. If we take a look here, we really need to stop having the head be on an unstable spring, to say the least. But you can kind of see like this is starting to be a more usable basic lighting solution as we go, right? Like that's actually pretty good. It's a little bit buggy because again, these reflectors are not, I like how much the spring is wigging out. That's very satisfying. We should just fix that. In Brain, there's all this crappy head code. So this stuff here, you know, we can cheese this out pretty easily by just saying like, okay, you know, the head DDP equals DDP. This code right here, I believe is really the entirety of our problem. What I'm assuming is that if we were just to clamp this, we would be okay. So if we did something like, if the length of this particular vector is, greater than, some max cap value, we'll just say that we're going to multiply it by the inverse of that value. So effectively, just saying that if this this length is greater than is greater than 0.1, then let's just make it equal to 0.1. I think that would do it. Looks like 0.1 is not quite large enough. Let's give it a little more than that. And so there you can see, like, I just basically clamped that spring down so that even though it's still a really ill-behaved system, it doesn't cause any problems now because it can't get unstable enough to lose control, right? So again, yeah, just looking at the lighting solution now, not good yet, but getting better, As we move the light around, you can start to see that it's, pretty reasonable. So I guess another thing I would be interested in checking, I guess am I in the Q&A now? I don't even know where I'm at. Let's see if we're at time. 9 minutes into the Q&A, okay. So if I take a look here and say, all right, the DDP is clamped, so we're happier now. If I go into world mode, and I wanted to create sort of another, give myself a little bit more to play with here in terms of occluders. When I do add standard room, if I want to sort of, in here play around with what's going to happen, what I could do is say, if offset y equals 2 or offset y equals, -2 or something like this. And in that scenario, now when I've got sort of these lighting corridors on both sides, basically, let me just go ahead and turn off the reflector view. So now if we take a look at what happens when I'm moving around, you can really see the shadowing start to be somewhat reasonable, right? Again, not great, but it's getting better. And so you can kind of see that we've got the surfaces behaving a lot more sanely, where if you take a bird's eye view of this and imagine we smooth it out and stuff when it's on the GPU, you can start to see how this would be a plausible, lighting solution, right? Let's take a quick look at what happens if we change the number of iterations on this. So if I come through here and I change the lighting iteration count down to 1, so here's just one pass on the lighting. in terms of light distribution. Let's crank it up to 3. Here's 3 iterations of the lighting. So another thing I'm interested in seeing also is what the emission amount does. 2 and 3 don't seem to do very much. I don't know why. That may be just a bounce issue. We'll have to look into that. Because, yeah, the difference between 2 and 1 is pretty noticeable. I'm wondering if, am I doing something wrong there? Like if, I wonder if I'm doing something wrong there. I might be. So I still think there's some bugs in there. That doesn't feel right to me. So we're still a little bit away, I think, from actually having a bug-free version of even the basic thing that we've sort of constructed so far. What I do want to do too here is I'm gonna do a quick change here of making 2 different colored walls as well, so we can play with that next weekend too. Let me just, actually I'll make that wall blue. So here you can kind of see 2 different wall colors now: a solid blue wall and a red one. And you know what I'd like to see eventually, what I'm not seeing yet, right, is I'd like to see, as we do more, I'd like to see more bounce lighting happening. I feel like right now it's really not. You know, I feel like this wall should be spreading out some more light there. Maybe there should be some mutual amount there. I'm interested in increasing the emission amount too. I want to take a look at that real quick. But I think we just have some debugging to do next weekend to really take a look more carefully at how that's working. So here's the emission values. What I want to do is, if we assume that 1 is the highest emission value and 0 is the lowest emission value, what I'd like to do is like max emission. I'd like to introduce the notion that there's some there's a, oops. There's a max emission value, and the max emission value is, you know, 10 or something. So a light of 1 is actually boosted. That way we can still transmit them more directly. So if you look at how much lighting is coming in now, right, it's a lot brighter, the light source is. And like that blue light is like, that blue surface there is really bright, and I would expect to see potentially some blue light kick out onto like these surfaces, and I am seeing a little bit, but only a little bit there. And so I'm interested to know why I see so little in terms of that, right? And I'm not sure. So I do wonder, like, okay, so if in config, if we increase the lighting bounce, right, I would expect to see that smooth out, and it doesn't really. So I do think that we're not really sampling very well. You know, we're still kind of crappy in terms of what we're doing here, and The reason I say that, like I said, is just because the difference between our first bounce and our second bounce is like nothing, right? So, looking at this here, this is with no bounces. It's just direct lighting. And when I go up to 1 bounce of lighting, I do get, a noticeable difference. When I go to 2 bounces of indirect lighting, I see almost nothing different about them, right? There's like no increased value. So I do think that there's a little bit, like we need to start thinking about our sampling and probably tighten that down more before we go any further forwards. Quindu, are there engine features or ideas that emerged during the Handmade Hero streams and that you've since backported to the 1935 engine? Not in terms of actual features, but there is one thing that happened on the Handmade Hero stream that I had not thought about before that I do use. It's the counter trick. So if you look back at Handmade Hero, there was a thing on stream that I realized where I was like, oh wait, if you are only using one compilation unit, then __ counter, the preprocessor macro, is unique for all the lines in the entire program. Normally it's not, because normally it's only unique per file. But in this case, it's actually unique through the project, which means that you can actually just know that every location where you use counter has a unique index into a table. And I do use that in the 1935 code base. And I'd never thought of that until Handmade Hero. It just happened on stream one time. I'd never seen anyone even think about that. I've never seen anyone mention it. I've never seen it even discussed. It's the first time, to my knowledge, that it's ever been done. Was on the stream. Now, maybe someone had done it before, but I'd never heard of it. And I use that now. Miblo, for the random series you picked at random 1, 2, 3, 4, could it have made any sense to pick 360 for 360 degrees, or would absolutely any number do? Oh, wait, is there a problem with the stream? No drop frames here. I think maybe someone else, unfortunately the stream got toasted. Someone else's, maybe internet had a problem, or maybe Twitch had a problem, I don't know. But anyway, what's happening there, remember, is that's just a seed value. So in the random series, we haven't really done any random number generation. So right now we just have a random number table, and eventually we'll replace this with an equation that generates pseudo-random numbers, right? So all that was is the seed value. So remember, we have an index into the table. We just are seeding into the table at that location. You could just as easily have picked 0 or something, right? Any number will do. It's just where you start in the table. And so because I didn't care what the random series was, that's why I picked 1, 2, 3, 4, right? But you could have picked anything. I wonder what happened. Did Twitch go down or something? Because my internet connection does not seem to have dropped anything. Like there was no loss in OBS at all, so it doesn't think it missed anything. Yeah, I'm guessing that it was just like Twitch ingest got toasted or something on the route got toasted. I don't know. Well, but then I should have seen dropped frames. So, right, because doesn't OBS report dropped frames if the ingest server knowingly rejects them, or it gets, you know, it doesn't get ACKed? So something happened in between Twitch receiving it and it going out, I guess. Is the only thing I can think of. Because it couldn't actually be a route being down. Because I would have seen the drop frames from that, I think. Right? I don't really know, but that's my assumption. And yes, I did see the tip on Visual Studio. That wasn't exactly what I was talking about. I know you can do that, but that's a thing that just saves one window. I thought there was a way to make it so that in general it just kept all the windows that you had open, but it doesn't seem to be the case, and I don't know why. It's probably something in here, I guess. Yeah, I don't know where it went to. Yeah, I don't know how you make it do that, but like at least on the one at work, it's in a state where it just keeps all the windows open, which is what I want. Whereas this one is now in a state where it automatically closes them. And I do not know how to make it stop doing that. So tools, options, environments, tabs, and windows. So tools, options, environment, tabs, and windows. Well, I don't know if else. Oh, okay. So this preview tab thing, that's what we don't want. Let's see how that goes. There we go. Perfect. Yeah. Because that was what was happening. It was coming up in that weird preview tab thing, and I don't want that. Thank you very much. Thank you, Big Fella Hull. That is exactly what I wanted. Big Fella Hull, not related to lighting, but I've been catching up with the multi-threaded sim regions tonight and noticed that we never unset the entity active flag if an entity is not contained in the updatable bounds. So I don't know what the status of that code really is at this point because it's a little bit nerfy. We never really quite figured out a way to keep those regions working when they get close to each other. So that was a little bit of a bummer. But so I assume you're talking about... Do we still have that? Flags. So it looks like so it looks like this should probably be, from what you're saying, I think you're right. This should probably be flipped, right? It should be... Probably be something like this, yeah? Where we say, clear the active flag if it's, you know, if it doesn't overlap. I guess the question I would have is, when does this part happen where mark brain actives? So that happens after it's unpacked. So yeah, so that should still work if we just clear it out that way, I think. We do have one problem here, which is we have nobody who's really active at this point. So let's see here. I think our world is too small for these things now, though. That's the only problem. They won't fit. They'll be crashy because they'll just be in the middle of geometry or something, right? I think. So what we can probably do, we probably can get the snake in there. So let's see. So if I said something like this, would that do it? There's a snake. Hello, Mr. Snake. don't know why snake has stopped. Oh, because it got locked up with its own tail, as is the snake's way. Let's make the snake a little smaller. So there's the snake hopping around. And I guess the other thing we should probably do, because if we're going to put the snake in there sometimes, we should probably have a way for the light to be, for there to be light in there. I'm just thinking out loud here. So, you know, if you imagine that you want to have these things have some sort of a emission possibility here. So I guess we've got I'm not sure how exactly we're doing the asset type. Let's take a look at entity visible piece. So entity visible piece has one of these things here. We could do like that, right? And we could say in here that whatever the test is for these, we could do that as well. So I could say like, all right, push a light on there. And I don't really remember what the values are for this, but let's take a look. So if I look into the render group under push light, you can see we've got the render group, the P plus the offset, we've got the radius, so we'll just use that. We've got the color and the emission, which I guess here we could sort of do. I don't know, we haven't really talked much about how we want to do these pieces here. So, you know, the emission can just be the dim y, I guess, in this case, because the dim y is not used for anything else. So we'll just sort of choose that at the moment and do it that way. So if we want to, we can now have lights on our entities, I guess. So if we make that happen, what we should be able to do then is when we construct these entities, so adds, I don't know, snake segment, what we should be able to do here is if we want to have them light up, we can. For example, I could just say that there's going to be a an add piece call for adding a light. So I could just do it this way. Say it's add piece light. The asset type ID at that point is irrelevant. And we just end up with the radius, the offset, the emission, the color, right? And so I think what we would get there is we end up with, for the pieces, we've got a piece type light. We've got the color value, just ends up being a v4 of color in 1.0. The offset is the offset. the v2 for the dimension is the radius and the emission. And the asset type is probably 0, honestly. I think that's mostly what we would need. Set type, dim, offset, color, and flags. That should be everything there. What is the problem? Trying to match argument list of entity, asset type. Oh, that's an asset header type. Sorry. Asset type ID. So in theory, I think that would work. I don't actually know, but we can try it. So let's suppose that I, just for sake of an argument, did add piece light here and did an entity. And I said that it was at, 0, 0, 0, I guess, or maybe it's slightly up from wherever the actual bitmap is. And then, yeah, I've got the color. Let's say it's a yellow light, because why not? And we got the emission value. Well, you know what else I need too? I need the radius. And then we have the emission value. Emission value can be, we're fairly weak light, maybe. Yeah. All right, so we've got radius, offset, emission, color. So that actually goes here. And so in theory, these snakes would have like little lights attached to them now, maybe. Yeah. So that's good. And that light probably wants to be up a little bit higher, but yeah, that's the basic idea. So if I just take this out, there you go. So now, if I move away, and we're just looking at the lighting from the snake, it kind of lights itself up. And we get into some of the problems that we're going to have as well when we look at this, because you can see there's some bad, we're probably going to have to treat sprites specially, right? Even in the future when they're a little bit better. But if we take a look at what the reflectors look like here, you can see that it's kind of a problem because the sprites themselves, the little snake sprites, are these huge reflectors that will shadow stuff underneath them unnecessarily. So that's definitely going to be a problem that we'll have to deal with kind of going forwards. Anyway. Let's see here. So, all right. So I think we're basically done. I'm just kind of screwing around at this point. Let's see here. There we go. And one of the things that I guess is pretty nice, right? And as we kind of go forwards, this is why I want a solution that kind of works like this, is you'll notice that it doesn't really, even though our lighting is pretty slow right now, it's happening entirely on the CPU, which is not what's going to happen in the future. And we're doing a bunch of sort of arbitrary stuff. if we can just spend another weekend or two getting the quality up to a good, reasonable point, we're still in a scheme that doesn't care how many light sources there are. And I like that aspect of it. So like adding the snake's light sources, even though there's 3, the number of light sources went up, it's 4 times what it was before. It doesn't cost anything more to do, because generally speaking, it's just the cost of the total number of things in the scene is the cost of the algorithm. It doesn't go have a multiplier per light source. And basically any global illumination scheme is kind of that way. Because global illumination is kind of assuming that all of the things in the scene are lights, in a sense, right? So that's good too. So basically, yeah, like where we're at right now is you know, yeah, you get the idea. I have, while we're in the hacking mode, I don't know, I'm kind of enjoying hacking on this. I'm curious too to know what happens if we turn off the ray detecting on after a certain iteration. So what would happen if we said that we allow light bouncing with no occlusion after you get to a certain point? So the first like 2 bouncers. So like if the iterations is greater than, you know, so the first iteration, second iteration happen with ray occlusion. If you get past that, you then are into just straight accumulation mode. At that point, so you know what does that look like? So you know here's what it looks like to just not have any of those happening, right? The number of bounces right now stays within there. You do 0 and 1, and then you stop. And now what happens if we add a diffusion pass after that, right? I'm just curious to know what that looks like. So it's interesting. It does send a lot of light around if you ever have a pass that that doesn't do the shadowing. I guess because at that point it's still able to take light from the actual light sources themselves. So you definitely, leak a lot of light at that point. All right, I just wanted to know for my own edification. All right. Oops. All right, I think I'll end it now. Let's see here. Brian asked, C-Tray license question, may I continuously update my GitHub branch of your timer code from Handmade Hero until you say otherwise, meaning you're preemptively giving me unlicensed public domain to any further code in that folder? Would you prefer I ask every time permission so you don't need to worry? No, yeah, you can just, I'll let you know if for some reason I ever don't want that code to be copied out. But yes, the C-Tray code you can copy out to your GitHub branch for sure. All right, let's close it down. Thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow the series at home, you can always pre-order the game on handmadehero.org. It comes with the source code so you can play around with it. Maybe you can play around with the lighting and find some interesting ways of solving the problems that we're trying to deal with right now. We also have a forum site you can go to if you want to ask questions, a Patreon page if you want to support the video series, a schedule bot if you would like to know when we're going to be live, and an episode guide you can use if you want to catch up on old episodes. That's it for this weekend. I will be back next weekend, I believe. I do have a move to do that may affect whether or not I can stream. I'm not sure, but probably be back next weekend, if not the weekend after, for doing some more improvements on the lighting quality. We're getting there. It's starting to feel pretty good, actually. It's just not at a good quality level yet, but it's starting to feel like we've got options. And we just need to start getting a little bit more serious about some of the ways in which we're computing the lighting transfer, and we maybe can make this work. So that's pretty exciting. That's about it for today. So hope to see you all back here for next stream. Until then, have fun programming. And I'll see everyone on the internet. Take it easy, everybody.